Hello again, this is Jeffrey Fox, and we're in the Big Data Open Source Software and Projects course, and we're in the unit devoted to big data applications and generalizing their structure, and this is the fourth lesson in this unit, Part D. And initially, we will just discuss. Actually, this is a review. These are a few slides you've had already. The components which we're going to feed into this analysis. And the patterns are going to be called ogres, mainly because the word giants has already been used for parallel computing. So we chose some related concept. And here is a slide we've seen before. It's as well as the 51 units we went through in significant detail, some of those in the last three lessons. We will also take input from this important work by Shantanu Jha and collaborators, which looks at 6 applications and divides them in terms of their capabilities. In particular, isolates the importance of data flow. Data flow is actually of growing importance because when you've done something, the next step is to join lots of such things together. And almost always that is data flow, because you have one job, it produces data, that data plus maybe the data from other jobs gets fed into a new job. So data flow is essentially guaranteed to be important. The only one which maybe isn't is this case here, where you have lots of jobs, but actually you're gathering statistics. You're doing one of these ensemble calculations where you do lots of similar computations to map out the possibilities that are possible for the climate in the future, given where we are now. But you see, everything else is data flow. And data flow, as I pointed out, is quite closely related to workflow. They're sort of looking at the same thing from different points of view. So this study did security and privacy, a brilliant study. This, I strongly recommend looking at the security and privacy work. And they identified use cases which we did not go through and analyze. They have important privacy. These ones are all privacy issues. We sort of mentioned web traffic analytics. Well, that's sort of a classic streaming problem. Health information exchanges. Well, we had lots of life science examples, including genomics, and of course, personal medicine is all connected with personal genomics. And how do you, there's a real challenge as to how you actually make progress in the field by the big data issues to join everything together, but that sort of has privacy problems. But in order to help an individual who may have a problem with that gene, you probably need to compare that gene with everybody else's gene. But if they're all private, you can't do it. Well, there's some pharmaceutical have special problems with trials. Cybersecurity is a key issue. I'm always getting persecuted by people having stolen my contact list and sending out spam to people who send me sweet messages saying, Jeffrey, you have a problem. So I have a problem. I don't know how to deal with it. The aviation industry is extremely worried correctly about privacy and security issues, because those are devices that cannot fail. We have lots of issues with, we know now drones are sort of now becoming commonplace just over the last 3 years. And they're doing all sorts of things from executing military action to just taking, inverted commas, just taking intelligence. And education, of course, is again fraught with privacy issues. This was a very important report, the NRC Massive Data Analysis Report. I strongly recommend it. It has, I think it's chapter 10, has the 7 computational giants. This comes from the part of the report which focuses on machine learning and statistics, and it identifies these key challenges, which I strongly agree with. That one needs to do basis statistics. That's what I captured with this feature called MR Stat. that there are lots of cases where you do statistics on the items in your big data, and then you need to gather those statistics together over the whole problem. That's a classic reduced problem. Huge numbers of algorithms are effectively order n squared, because in the case of data, you have some locality, namely if your data is, say, friends on Facebook, probably most of your friends are nearby, and both geographically and in other senses. And so there is some locality with some of the data, but other data like genes, any one gene can be aligned. I mean, or at least you can look at how one gene aligns with any other gene. So there is actually a relationship between all pairs of genes. So that's an order n squared algorithm. Graph points out that when you take things, say, like Facebook friends, or you get a very complex relationship between the different points in that space of friends, and that leads to a graph. That graph is very complicated. It tends to be somewhat more complicated than the relationships we get from the simulation world, where they're sort of more controlled. A given particle interacts with all particles a certain distance from it. So there's a much easier way, usually, of characterizing the relationship between items in a simulation, in a large-scale simulation. Huge number of problems are dominated by linear algebra. And that's key to be able to do linear algebra very fast. I mentioned the case of the deep learning. Deep learning is dominated by matrix-matrix multiplication. That matrix-matrix multiplication runs like a bat out of hell on GPUs, and that's why GPUs are very good for that problem. We have all sorts of approaches to optimization, like linear programming, dynamic programming, and those need to be supported for the big data. And that's a broad sort of area which is not so easy, because actually linear program doesn't parallelize very well, because it has constraints, and how you do those constraints doesn't work so well in parallel. On the other hand, this one here is, to me, one of the more interesting to me, is what I call global machine learning. Here you have a giant set of entities, all the world's people, all the world's books, and you want to then do some analysis, like to find out the hidden factors or topics for your news page or something like that. And there you use these algorithms like mixture models, latent Dirichlet allocation. These are all related, clustering. These are all sort of similar algorithms that are trying to take spaces and chop them up in some fashion, or find out what's the underlying space hidden in that thing. And then another important class I've actually mentioned on the previous slide, on the gene case, you often have a set of data, and then you take a new point, like a search, and you need to compare that new point with all other points. So those are sort of alignment problems. In the case of genes, often that's done with BLAST. You take your new sequence, and then you do a BLAST analysis with a collection of other old sequences. So that's an alignment problem. It's different from what you're doing here, which is not aligning, but you're doing some ab initio breakup of a problem. So what we're trying to do now is, we've gone through lots of examples, we've looked at lots of general features, and we want to capture the essence. Because if you want to understand what's going on and whether your computer's any good for doing big data problems, you can't run all applications, so you better do something about that. So we need to capture the essence of these use cases and say, all right, if you can do these parts of these use cases, you're in great shape. So this gives you things like kernels, the core essential part, which takes all the time. So-called mini apps, which applications cut back to allow you to do realistically, put them on new computers to see how well they work. Another thing you can do, which is to classify the applications into patterns or groups of related applications. And we're going to do a little bit of this analysis, and say it builds on this earlier thing I referred to, which was summarized in these talks, but done in more detail in this old section 5 of my analytics and applications class. And I also point out that I am not a database expert. I use data continuously, but not traditional relational databases. and I'm a great expert, or probably too much of an expert, in high performance and parallel computing, and so that gives me a huge bias. Well, that's actually the way the world works. You take people with, best thing is interdisciplinary work. You take people with different biases and bring them together. But here you only have one person. You have my biases. So if we look at the way things that people have done this in the past, there are some famous in the area of parallel computing or high performance computing. We have some famous benchmarks. The most famous is LIMPAC, which is technically HPL, which is a parallel full matrix solver using the so-called LU factorization method. Lower upper matrices are used, and it's used for solving linear equations. And this benchmark is used on all supercomputers. And the so-called top 500 ranks computers on how fast they are on LIMPAC. Now, a somewhat earlier concept of LIMPAC, which was the so-called NAS, which was a unit of NASA, parallel benchmark, very important piece of work, which introduced, and you can see 8 kernels. These are sort of kernels. They're nuggets of code which summarize features of applications. Most of them are sort of typical solvers. Multigrid is a solver. Conjugate gradient is a very important solver. Fast Fourier transform, it was a solver/algorithm. Integer sort is an algorithm. This is a little different. It's the so-called pleasingly parallel. It used to be called embarrassingly parallel in those days, until we realized that most problems were actually embarrassingly parallel. So it didn't seem very sensible to use this slightly degrading term, so pejorative term. So we renamed them pleasingly parallel. That's the same thing as embarrassingly parallel. Okay, I'm very good at writing, aren't I? Then we have, these are other rather more complex structures for solvers, block tridiagonal and scalar pentadiagonal. This is just matrix structures. And here we have the LIMPAC, LU. No, not LIMPAC, it's actually low. It's LU, it's symmetric Gauss-Seidel. Gauss-Seidel is not LIMPAC. It's an iterative approach to solving linear equations. All right, and now perhaps the most famous parallel computing approach was from the incredible group at Berkeley, who had this Berkeley view of parallel computing, which included the Berkeley dwarfs. It's built on a very distinguished scientist's work at Berkeley, Phil Colella, who invented 7 kernels, which was slightly different level, higher level than the NAS parallel benchmarks. Summarizing, each of these has many different methods of solving them. He had Monte Carlo, which was dropped from the Berkeley dwarfs, and then Berkeley added a whole new set of things like MapReduce, combinatorial logic. Here we have graph, dynamic programming. We sort of mentioned that, remember, when we did the Computational Giants. Branch and bound is a well-known optimization method used a lot in doing things like aircraft scheduling and things like that. Graphical models and finite state machines. So these are actually represent pretty broad spectrum of things. They're not even the same category. I mean, you could argue MapReduce is a runtime or programming model, and spectral methods are a numerical method, and linear algebra is a computational approach, and so on. They're very different. So actually, we draw from this. If Berkeley, which is the center of the world, came up with this complex, multifaceted thing, then we can only hope to do the same thing. So we're going to use this as an excuse of being rather complicated and not having a clean classification. So now we finally come to this classification, which actually builds on the features we've already done, and just re-list those features from viewing them as patterns, not as features. So here we have the so-called problem architecture facet. So here we actually, this is work done with Shantan Nijjar and Judy Chu, and we are trying to made more explicit than people have in the past. That when you look at the characteristics of a problem, you actually have to look at it from different points of view. So we call those points of view facets. So, and the ogres are the overall patterns. And those ogres have what I call micro patterns, which are the very detailed kernels, the mini apps. But they also have what I call meta patterns or macro patterns, which are the overall structure. And I put pleasingly parallel as a overall structure. And we know that goes with local analytics and local machine learning. We have classic MapReduce, which is used for the search index and query, classification algorithms, collaborative filtering, the MR stat, which is G1, and also the G7 area from those computational giants. We have global analytics, which is iterative programming models, typically maximum likelihood or chi-squared minimizations. I published my first paper on chi-squared minimization 50 years ago. And an important technique from Durbin is called expectation maximization, which often involves iterative steepest descent approximations to a problem. When you're doing optimization steepest descent, which says where you are, you go in the direction where the function decreases most rapidly, is a very important technique. What you have to do is to do it cleverly, because if you just do that, you'll get stuck in the local minima. But if you do that ingeniously, choosing that direction adaptively, so to explore the different aspects of the problem, and you make certain you don't move too fast, because if you move too fast, the linear or quadratic approximation you were using breaks down, and you'll get total nonsense. So you have to never move too fast when you're doing optimization. Remember, here we have the graph things, problems being set up as a graph. Here we have an important concept originally coming from Federico de Rima from IBM called single program multiple data. Most big data problems are set up in that fashion. You have essentially a single program. You're running it in parallel. Those programs are replicated, but they use different data. Here we have what I used to call loosely synchronous, but that didn't catch on. And people tend to use the term bulk synchronous processing, which says that the world is divided up into compute communication phases. And you iterate that iterative MapReduce, and you actually just do one phase of MapReduce, because here's map is compute, and reduction is essentially the communication phase. Fusion. I had fusion earlier when I was doing the intelligence applications. The last step is usually fusing data from lots of different sources together. That's a little different from data flow. Data flow is often internal to a particular area, and you flow data between the different components. And then the final thing I have here is using agents, and agents are a particular approach to computation, and they're used in particular in epidemiology, and another well-known approach is called swarm approaches. Related to those macro things, these are also sort of macro features. They're more quantitative. How many flops, how many floating point operations do you do per byte read from memory, per byte read from disk? Because unless you do lots of floating point, you're going to be dominated by memory access or disk access accordingly. Another important aspect is how much communication do you need, and of what type is your communication? Like MapReduce, so global reduction operations or broadcast operations, or is it like it is for solving differential equations, where the communication is local? Each node communicates with other nodes which are local to it in whatever space this problem is set up. Almost every problem can be thought of as having a graph, because even when you don't, even whether you have differential equations and you do some finite difference, you have points linked to each other. That's a graph. It's a very simple nearest neighbor graph, but it's still a graph. And there are important cases as to whether that graph is constant or dynamic. So the other issue, this is variability in time. We also have variability in inverted commas in space, where space is the space on which the problem is defined. And then we have important cases of what we used to call homogeneous, which is regular structure in space. That's what you get from a finite difference, simple finite difference approximation, or pixels of an image. Or is it a complicated irregular graph which you'd get from Facebook if you had looked at the friends relationship? And we also had various styles of communication, bulk synchronous processing, asynchronous, that's you often get when you do thread-based systems. Pub/sub is very important for streaming problems. Collective, that means that all the nodes communicate with all the other nodes. And that the flip of collective is point-to-point. Points connected to talk to each other in node A talks to node B specifically, and it labels B as the where it wants to go to. We've need to know whether the algorithms are iterative or whether they, which is what you get when you do parallel linear algebra and things like that, or parallel differential equation solvers, or are they just like MapReduce? They do essentially a single map or compute in a single communication, and then they stop. Well, we have the question about the importance of data flow. I've already said I think data flow is very important in most cases. Another interesting area is the so-called data abstraction. Is that we know Hadoop is largely set up a key value, but if I do other areas, I'm going to want pixels for image processing. I want graphs for graph problems. Other problems, I'm going to want vectors or matrices. That's the deep learning case. Also, we need to know how are the data points set up? Are they living in a Euclidean metric space? Or are they just sort of random points in without a metric space? If I look at collaborative filtering with users and items, those are not Euclidean spaces. They're just general spaces with actually most of the coordinates undefined, because most items are not ranked by a given user only ranks a few items. I already pointed out the order n squared algorithms are very important. Other algorithms are order n, and where we have m points per iteration, that's a very important point. And then we need libraries. Like a lot of problems, you need the linear algebra libraries, conjugate and gradient, full matrix, reduction libraries, broadcast libraries. That's all very important.